Welcome everybody to Air Filtration in Travel in 2022 and NAFA's Talking Air Filtration series. My name is Tony Verhoeven. I'm the Director of Marketing at the National Air Filtration Association, and we have assembled an awesome set of panelists here, experts from all over the industry. In air filtration and in travel. So I think you guys are in for a treat. So I will save the introductions here for Jeff Thibodeau, who will do the introductions, and I'll just do a quick overview. If you're here and you're not sure who NAFA is, I'll give you a quick overview of who that is. And who's putting on this webinar here. NAFA is the National Air Filtration Association. We are about 1,000 people and about 350 manufacturers and distributors of air filtration products. There's no better place to be. If you're in this business, you really should be here. One of our former presidents has a great quote here that says that relationships forged in NAFA justify every dollar spent on dues. So we focus in on expertise, education, and best practices in air filtration. Check out our website. You've probably already been there for a lot of great content surrounding air filtration, science, and application. We do have a lot of training and education. So next month, we will be putting on the bag in, bag out NCT NAFA Certified Technician Level 2 certification. This is where you are suiting up and removing a filter with removing a filter with possibly hazardous materials or bio stuff in there that you don't want to mess with here. So good training there that you might want to look into. We are looking also for thought leadership and subject matter expert. This is a picture from our recent technical seminar. We are always looking for great speakers. We've got some great speakers here that we have spoken before at our conference, and we get a treat to be able to also hear them again. So if you are a subject matter expert in air filtration, we want to hear from you. Go to our website, nafahq.org, and go to under events, and you go down here, the open call for air filtration thought leadership. So that could be in a webinar, a video, a podcast, a paper, an article, an in-person sort of topic. So leave it up to you and how you want to present, but we do want to hear from you and start to learn more of what other expertise is out there. So please do take the chance to submit something. And if you want to keep in touch with us, we're all over the place. We'll turn this into a podcast. And if you want to listen to our webinars and some other interviews, we've got that. And then we also have YouTube and Facebook and LinkedIn and all the usual suspects of places there. So again, thanks for your attention. We're going to go ahead and turn it over to Jeff. Jeff Thibodeau is from Micropore, and he's going to be our moderator for this session. Jeff, take it away.
Thank you, Tony. Happy to be hosting today. I do have a little bit of a voice issue, so I'll do my best Demi Moore impersonation and run through this. But very, very privileged today to have three guests, Richard Gillick, Dan Fillenworth, and David Space. All three are experts in travel and air quality. Quick bio on Richard. He got his BS in Business Administration from the University of Nebraska, Lincoln, and an MBA from Norwich University. He's an indoor air quality professional with Dynamic Air Quality Solutions, where he's responsible for commercial sales and engineering support. As an IAQ professional, Richards had addressed many industry trade groups and associations about indoor air quality, energy savings, maintenance, sustainability, and facilities management issues. And prior to joining Dynamic, Richards served 11 years as a United States Naval aviator. So thanks for your service, Richard. Dan Fillenworth, BS Mechanical Engineering from Purdue University. He worked for a major commercial HVAC equipment and controls company for 17 years, co-founded an HVAC commercial equipment manufacturer's representative and temperature controls company, retired from that after 12 years, and in 2020 founded Luminaire, which focuses on air quality in public spaces, specializing in transportation. David Space, some of you may have met David or heard his presentation at NAFA Technical Seminar in Louisville. He was the lead engineer and associate technical fellow in the Environmental Control Systems Organization and was with Boeing for 33 years. He's the former chairman of ASHRAE TC 9.3 Transportation and Aviation Research Committees, vice chair of the SAE E31 Bleed Air Panel, member of ICAO 344 and SAE AC 9M committees, and a founding member of ASHRAE Air Quality Standard 161P and EU AECMA-STAN Air Quality Committees. So privileged to have three fantastic guys with us today, and I'll let them roll with it. Dan, I believe you're up.
Thank you, Jeff. So I just wanted to start, go ahead, slide. Start with the importance of public transportation. Millions of people rely on public transportation every day to get to work, to school, grocery, doctor, etc. The FAA tells us there's 2.9 million air passengers every day. The APTA says 56.1 billion passenger miles, split roughly 50-50 between rail and bus every year. And more than 25 million students get to school on school buses every day. Slide. So public transportation, as we know, is safer, it's less expensive, it uses less energy, and is more efficient than automobiles. Slide. People density is inherently high in public transportation settings, and that creates unique transit-related indoor air quality issues. Slide. So let's compare the density in a metro bus to a commercial office space. Slide. Using pre-COVID square feet per person for an office space, the density in a full metro bus is like having 1,120 people in an office made for 40 people. As the return to workplace continues, people are looking for more space per person, not less. Can you imagine the density in a full metro bus being 28 times more than pre-COVID office density? Slide. Similarly, a school bus 2/3 of the way full is like having 275 kids in a 25-person classroom. Children get off the school bus and are told to spread out, stay 6 feet apart as they enter the school building. And classes have been scheduled to minimize crowding in classrooms as much as possible. Can you imagine how parents and teachers would feel if they were told there would be 275 students in a 25-person classroom? Slide. So why make that comparison and talk about people density? Well, people density is important because infection is a function of concentration of contaminants in time. This visual from the New York Times shows an infected student breathing out droplet nuclei that contain viral matter. Slide. If nothing is done to reduce the contaminants that the infected student breathes into the air, they will quickly fill the space, and disease can be transmitted from that infected student to healthy people. This goes not only for COVID-19, which unfortunately is again on the rise in the United States, but other respiratory diseases like the flu, RSV. Slide. So how do we reduce the concentration of contaminants? We can either dilute air in the space by replacing it with outdoor air, or we can filter the air in the space to remove contaminants. Some important terms I just want to touch on are equivalent outside air or equivalent outdoor air, which is space air that has been cleaned to match outdoor air, which we assume to be free of contaminants. I'll touch on that later. Another term is air changes per hour. So when we're speaking about air changes per hour related to indoor air quality, we're speaking of clean air that's circulated through the space. Sometimes you'll hear air changes per hour, and it's just air that's moving through the space. So just moving dirty air around through the space doesn't reduce the concentration of contaminants in the space. And finally, clean air delivery rate, which is how much clean air an air cleaner produces. Slide. An issue specific for transit is the quality of the outdoor air. The buildings have requirements for specifying that their outdoor air intakes are not located near the road due to the pollution along the roadways. Vehicles are hopefully right on the road, where outdoor air contains higher levels of particulate matter, carbon monoxide, and other pollutants. Slide. Another issue with using outdoor air in transit is the HVAC system capacity associated with cooling and heating outdoor air. Transit HVAC systems have been optimized to be small and lightweight, as their HVAC systems must be carried with them. If we were to cool air from Tampa outdoor air design conditions, we would need 4 times as much capacity as cooling air that's already been conditioned. Similarly, heating air from 0 degrees Fahrenheit requires 4 times as much HVAC system capacity as if we were heating air that's already been conditioned. So that flies directly in the face of what our goals of better miles per gallon, extended range of electric vehicles. It makes it difficult to use outdoor air to reduce contaminant concentrations in transit settings. Slide. You know, I found that in my experience, passenger rail HVAC systems do use outdoor air similar to commercial buildings. They have return air and outdoor air dampers, and that air is filtered. However, typically metro buses and school buses don't bring outdoor air in. And I don't mean some, they don't bring any outdoor air in through their HVAC systems. And for the reasons stated on the previous slides, I don't think they will be in the near future. So since outdoor air is not the solution, and we must rely on filtration. Slide. ASHRAE's April 2022 issue provided a prescription for evaluating air cleaners. Air cleaners can be described as either subtractive or additive air cleaners, and the effectiveness of both can be measured and defined in terms of clean air delivery rate, or CADR. It's also important to evaluate how that clean air is delivered to the occupants. Slide. This chart shows the effectiveness of different MERV-rated filters in removing airborne droplet nuclei. Remember from earlier that we're trying to reduce the concentration of contaminants in the space. A MERV 13 filter removes 87% of droplet nuclei based on particle size distribution shown, which is what humans generate when they exhale. The CDC says to increase filter efficiency as high as possible. MERV 13 filters are recommended by ASHRAE. The U.S. Environmental Protection Agency just recommended MERV 13 filters in its Clean Air in Buildings Challenge earlier this year. And I think as you can go higher in filtration efficiency, the better. Slide. How about additive air cleaners? Additive air cleaners put substances into the air to destroy contaminants. We're not going to talk, I think at this point, about some other substances that could be created with those additive air cleaners. Let's instead focus on the clean air delivery rate that they can provide. And this chart that's on the right from ASHRAE Journal can be used to calculate clean air delivery rate for additive air cleaners. Slide. So let's look at the example of a transit HVAC system at 2,400 cubic feet per minute, which would be a typical metro bus situation. And let's calculate the clean air delivery rate, or CADR, for both a subtractive and an additive air cleaner. In this case, we'll look at an MERV 13 equivalent filter and an additive air cleaner that was lab tested to, quote, reduce greater than 99% of SARS-CoV-2 in 1 hour. Slide. For the MERV 13 filter, the clean air delivery rate is simply 87% times the amount of airflow through that filter, which gives us a clean air delivery rate of 2,088 CFM. For the additive air cleaner, we use the chart at the right to find the intersection of time and percent effectiveness to give us 0.09 CFM per cubic foot. Then we use that number and multiply it by the test chamber volume to come up with, in this case, 90 CFM. That's a dramatic difference, which may be surprising to some people. There's also an online calculator that I want to mention on Portland State University's website, which allows you to consider how much natural decay occurs without the additive air cleaner on, and then calculate the numbers that I show in the chart. Slide. So just a summary so far, public transportation is necessary. It's widely used. People density is high in public transportation. Disease transmission is a function of contaminant concentration, which goes along with that high people density. And outdoor air for reduction of contaminants has limitations we discussed in transit. So filtration in transit is imperative. And due to the points above, especially the people density and lack of outdoor air, we should at least try to achieve the levels of filtration dictated for public buildings. With that, I want to turn over the presentation to Rich.
Thanks, Dan. So high efficiency filtration. Can you guys hear me, by the way? I just want to make sure. I'll take that as a yes. High efficiency filtration brings with it its own set of challenges. Increased pressure drop is going to require higher fan speed to maintain airflow. Most often, the fans are limited to speed, so the consequence is reduced airflow. This has other drawbacks like reduced performance and potentially frozen coil. The choice has been really either use substandard filtration or have higher maintenance requirements, assuming your fan can handle it. Because of this, many in the industry have limited their media to MERV 7, which is really unfortunate, just as Dan showed earlier. And that's assuming, again, that the fan can handle even that level of static pressure. Slide. So just to show you, here are some of the filtration that we've seen in the industry. You can see everything from a MERV 2, MERV 4, and MERV 7, which are that passive filtration that is being currently used in the industry, or was being used in the industry, kind of phasing that out. We've heard from one public rail customer who has switched to MERV 13 that now they're being forced to change their filters every week. So as opposed to being able to extend that out at least months, now they're down to every week they're doing filter changes. Slide, please. Other customers have switched to what's known as polarized media. Polarized media is still a subtractive technology that combines a passive medium with polarization and agglomeration. So as you can see here, and as the video plays, there's still a media there. And as the particles come in, this polarized media, they add electricity to it. And so as particles come in, the particles come in negative first, positive out. And so they're able to form all the way around every fiber. And that's going to give the customers or the users three benefits. Maintenance savings, because the instead of just loading up front, you're going to load 360 degrees around every fiber. You're going to have energy savings because the fibers don't have to be as close together, and you're still getting that high efficiency performance. Next slide, please. And so you can see here where a passive filter is only loading up front, whereas this polarized media is loading 360 degrees around every fiber. Now, I told you there's three benefits with this polarized media, the third being agglomeration. Now, what agglomeration is it's polarization at a sub-micron level. As it turns out, the smaller the particle, the more the polarization acts on it. And so the really small stuff is not only binding with the fibers, but they're bonding with each other as well, other particles as well. And so you're turning small particles into bigger particles and making them easier to capture, especially in a recirculated environment like public transit. Slide, please. So before we start this video, let me just explain what's going to happen here. And so what this is a polarized panel in a very small chamber. And inside that tube there is a cigarette. And what they're going to do is they're going to pump it up with smoke. So go ahead and play the video now, please. And so you're going to see as he's pumping it up, obviously cigarette smoke, we're all familiar with it. We're all familiar with how all the problems with it, but it shows how well you can get that smoke filled in there. Now, the first thing he's going to do is he's going to turn on a fan. And so that fan, all it's going to do is circulate that air throughout the media. And you can see there, without the electrical charge, nothing's really happening. But once he turns on the electrical charge to the media, you can see here, the media is able to quickly draw those smoke particles out of the air. And so this is a good visual on essentially upgrading passive filtration with electricity to create that polarized field. And this is what you're able to see. Now, for the customers that are dealing with those the fires on the West Coast, this has been a game changer. But it also shows for those people who want to breathe clean air, this is a good solution for them as well. Next slide, please. So how do these MERV 13 equivalent filters perform in a transit application? A customer had an air balance. So one customer in particular decided, you know what, instead of putting in sensors to say, hey, what's my pressure drop upstream, downstream, I really just want to know what's my airflow. And so they had an air balance contractor come in and test their this new polarized media against what they were using with their MERV 4 when it was brand new. And then again, this customer happened to be doing change outs. This was a transit customer, a bus customer. They were testing it out every 3,000 miles. And they were normally changing out their MERV 4 media at 3,000 miles. And so they tested out the polarized media at 3,000, 6,000, and it took up to their 9,000 mile mark before they saw the same pressure drop as the MERV 4. So what am I saying? I'm saying that they were able to get 3 times the amount of maintenance life before they got before they reached the pressure drop of their MERV 4 media. Next slide, please. So, and again, this is just to show that air balance shows that at 3 times the standard rate, they were still able to achieve that MERV 13 performance. Now, other transit companies, instead of using 3,000 miles, have used 6,000 miles. And my understanding is that they're still able to see that same level of airflow at the 18,000 mile mark. Next slide, please. Excuse me. So here's some pictures. The one on the right is obviously, this is the back of the bus. And on the left, taking off that panel, you can see that filter media in there. Now, the polarized filter frame, that metal frame all around there, is stays with the bus or the train, as it were, and it's just the media that gets changed out. It's that white part that gets changed out. Next slide, please. And so now we're going to look at, we looked at a bus. Now let's look at a rail installation. You can see where those guys are standing on that picture on the right. That's where the return is, and so that's where they elected to put to replace the passive filtration with the polarized media. Next slide, please. And so a closer view, that's that return grate on the right, and on the left is the polarized media. Now, the train, the rail company that did this decided that they not only wanted to use UV, they didn't want to use just the polarization, they also wanted to use UV as well. And with this polarized media, they're able to do that in conjunction because it is a glass-based media, so they're able to do combine it with UV. Next slide, please. So in summary, for at least the rail and bus portion, public transportation is obviously necessary and is still widely used. People expect that not only when they go into public buildings, but in public spaces in general and in public transit, that their air is going to be clean. And people are becoming more and more aware of the questions to ask and are really starting to think about what that air quality means. And so they're asking the questions, and it's incumbent on building owners to provide what their customers are expecting. And the people density and outdoor air quality, whereas, like Dan said, a lot of times you would position your air intakes to keep the dirty air away from your intakes. Well, a lot of times that means highway air, and hey, we want to keep all that away from my intakes. Well, when it's public transit and trains and whatnot, you're in and amongst it, as well as you're producing some of that that pollution yourself. So you can't get away from it. Higher efficiency filtration is difficult, but not impossible to achieve. And so with technology out there, we really need to, and customers are really starting to see that they need to provide what their customers are asking for us, and especially with this higher efficiency filtration. With that, I will pass it along. Thank you very much.
David,
go ahead. Next slide. Can you hear me okay? Okay. So I'm going to start talking on aircraft filtration, but I'm going to start with talking about the operating environment of the aircraft itself. So when the aircraft is in flight, 36,000 feet, it's a very hostile environment. It can be very dry, less than 1% relative humidity. Very cold, minus 45 degrees Fahrenheit, minus 43 degrees Celsius on a warm day, minus 85 degrees Fahrenheit, minus 65 Celsius on a cold day. Very low pressure, less atmosphere than at the top of Mount Everest. Airplanes fly higher than 29,000 feet. And depending on the latitude, altitude, and the time of the year, you can also experience elevated ozone. So to operate in this environment, we need to have an advanced environmental control systems. And next slide, please. So that's kind of a separate topic unto itself, but since this discussion is more on filtration and air distribution, spread of disease, I'm going to kind of keep it centered there. So I'm going to talk about our cabin air distribution system. This is a typical cross-section of an airplane cabin. You can see at the very top is the overhead air distribution duct that runs the entire length of the airplane in the overhead. And then depending on the airplane, you'll have two air supply nozzles that also run the length of the airplane, sometimes along the sidewall, sometimes from the center. So that depending on the airplane, you could have 2 to 4 overhead air supply nozzles. And the air comes in from the top, it's exhausted from the floor through return air grills. It's on a continuous basis. Half the air coming into the cabin is outside air, so really quite pristine at 36,000 feet. And the other half of the air that comes into the cabin is through HEPA filters. And that's on a continuous basis. So the air leaving the cabin, half of that's dumped overboard, half of that air goes through the HEPA filters, and it's just continuously flows that way. Because of the temperature control we need to maintain during cruise, we need to have fairly high air exchange rates. So our air exchange rates on the airplanes average 20 to 30 times per hour. So quite high to be able to do that. Next slide, please. So let's talk a little bit about filtration. Our first filtered aircraft was a Stratocruiser back in the 1940s. Very coarse, basically metal mesh for keeping big things from going into the fan. But in the mid 80s, the 767, the 757 came on board, and we had HEPA type filters on there, 2-piece filters, a pre-filter, and then a HEPA type filter, about 95% efficient, I think about a MERS 16. And working with the suppliers from that time frame, we were able to improve their internal processes and increase the efficiency of the filters to the point we were able to get up to true HEPA filters on our production airplanes. Next slide, please. So you'll see on the airplanes today, including Airbus aircraft and Boeing aircraft, in the research systems, those are true HEPA filters, essentially able to remove all the particulate matter from the research air, including single viruses, bacteria, and tobacco smoke. Where there's a little bit of a dip in the curve is around the 0.1 microns to 0.2 microns. But even there are 99.9% plus efficient at removing those particle sizes. And the efficiency goes up for smaller particles and larger particles. And that gets into the capture mechanisms that HEPA filters use. All right, next slide, please. So let's talk a bit about spread of disease on aircraft, an area of real interest. When COVID first hit, air travel dropped 50% domestically and over 70% internationally. So it really impacted the aviation industry tremendously. Next slide, please. So there was a big study done by the Department of Defense called Transcom, and they wanted to look at the risk of spread of disease in aircraft. So if somebody was to cough or sneeze, if you're sitting next to that person, what exposure would you see? Or if you're sitting several seat rows in front or behind, what type of exposure would you see? And they were looking at it from the perspective of potentially using commercial aircraft to transport military folks. And so they were concerned about that. And so they did 8 days of testing. They did risk assessments. And so I'll kind of walk through some of the testing and some of the results that they show. And they did breathing and cough scenarios for both. Next, please. So this slide shows their test equipment and methodology. They used, you can see the head in there, they used a breathable mannequin that could breathe out, simulate a cough or simulate breathing. And then they used what's called IBACs, instantaneous biological analyzers, where they can put it in the same seat row as the mannequin, the index case, or they can put it multiple rows in front, multiple rows behind. And so they ended up using 42 IBACs each time. So they could basically surround the index case. And they did this in the economy section of the airplane, the business class and first class. And they did over 300 releases. Each release was 180 million fluorescent tracer particles that were released to the air that could then be detected by the IBACs. The particle sizes were 1 to 3 microns. And they also wanted to look at surface depositions. So they also did some TEG tracers to measure aerosol depositions as well. Next slide, please. So this is some of the actual data. It's small, so I'll kind of explain it. The red box is the index case. So, 100% of the contaminant is coming from that 180 million particles being breathed out. Surrounding that is the amount of particles that have penetrated into the personal breathing space of that particular passenger. So that IBAC was set at that breathing height for inhalation. And what they found was that even in the worst case out of all these test simulations that they ran, the 300 tests, 99.7% of the particles do not penetrate the breathing space, even if you're sitting adjacent to the index case. Only about 0.3% did. If they looked across the aircraft, so all 42 seats, 99.99% simply the particles didn't make it into the breathing space of the adjacent passengers, either sitting adjacent or forward or back. And their conclusion was on aircraft, because of the very high air exchange rates, the rapid dilution, the fact that airflow comes from the top and is exhausted down, so there's a continuous push of contaminants downwards. The HEPA filtration, so that what comes through the research system is essentially particle-free air, all play a part in minimizing contaminants. And surface contaminants was also, they found to be minimal. The very bottom, you can see kind of how they set up the IBACs. In the economy section, they did the same in the mid and the forward parts of the airplane as well. Next slide, please. So kind of conclusion of that study, we did see that the results matched really quite nicely with our computational fluid dynamics modeling. Working with the Harvard folks, they've also done some epidemiological studies. Those matched up nicely. As I said before, maximum exposure nearby was 0.3 out of all the testing. In other words, 99.7% did not make it to the breathing space from all the testing. And then the study compared the air exchange rates and time to remove 99.9% of the particles released. And so if you look at a typical home, 4 air changes an hour takes, a little over 100 minutes. Operating rooms, isolation units, about 12 air changes an hour, take about 35 minutes if a person coughs to remove 99.9%. The aircraft, this was a 767 and 777, both wide body aircraft. Much quicker, 6 minutes or less. Standard body aircraft, more narrower aircraft, tend to have even higher air exchange rates than the wide body aircraft. Next slide, please. So kind of the reasons why we're seeing the results that we're seeing is there is some unique design features of aircraft. As I mentioned, the high air exchange rates. Every 2 to 3 minutes, typical building is 2 to 5 air changes per hour rather than minutes. Our airflow is from ceiling to floor. That tends to push contaminants down and out. So there's continuous push that direction. The high efficiency filters used. And then the seats themselves, we've seen from our modeling, serve as a barrier to a degree. If somebody's coughing or sneezing, it kind of channels, keeps the contaminant in that area. And then we also design and balance the airplane so we minimize the airflow in the fore and aft direction of the aircraft as well. So Harvard University, several of the professors there had a panel that they put together, and they looked at all the scientific evidence. And their conclusion was very low number of infections could only be attributed to exposure on aircraft. And they came to the same kind of conclusions. What are some unique design features that help to minimize the spread of disease? Next slide, please. So there is another type of filtration that's becoming more apparent and more important, I think, that is going to move into aircraft. And that is air purification. It's a technology that I think is there. It provides a real benefit, and I think is going to help to move to performance-based regulations. So I'll talk a little bit about this. Next slide, please. So there was a big study done by ASHRAE. I think this was the biggest study done by the ASHRAE. ASHRAE is an organization that sets indoor air quality standards in indoor spaces. There is a committee, 161P, that does that for aircraft. And this was a research project where it was with multiple airlines, I think 3 different airlines, many different aircraft type. And they utilized questionnaires to measure comfort and health symptoms. And then at the same time, they took measurements to look at environmental measurements, individual work-related factors, health factors of individuals, and looking at relationships. This was carried out by Battelle and the FAA Centers of Excellence for Aircraft Cabin Environmental Research. Boeing was a sponsor of this research along with the FAA and the ASHRAE organization. But what it shows, and this is really fairly consistent, you can go back 20 years and look at some questionnaire research, and it shows very consistent data. That if you look at the primary symptoms of passengers, you're looking at symptoms of the eyes, nose, and throat, the dryness or irritancy of the eyes, nasal stuffiness. There is some seat-related symptoms, back pain, stiffness. But same thing with the cabin crew. There's some really good studies that have been done on cabin crew showing very similar symptoms, irritation to the eyes, irritation to the nose, to the throat. For multiple flights a day, shuttles, then you also get into some pressure issues on the intestines going up and down. There is some bloating, cramps, and so on. Okay, next slide, please. So here a few years back, we went to the Technical University of Denmark, where they're one of the leading universities in the world for air quality research with human subjects. And we did 4 years of research with them. And we wanted to look at the effects of different ventilation rates, temperature, humidity, and air purification technologies. And one of the things we learned is we could very readily simulate the same types of symptoms that people see in flight. In other words, we're able to key in on producing a similar contaminant signature, used carpets, used seats, people, high density. And we were also able to look at the benefits of air purification technologies. And so if you look at this bottom right chart, with high outside airflow, you get low humidity, right? Because the air coming in is less than 1% humidity. But you're going to get more symptoms due to humidity. That's this blue line. So up is worse on this graph, but you'll also have low contaminants. And what we wanted to do, and what we did do, is we reduced the outside airflow from 20 CFM outside air all the way down to 3 CFM outside air. And at the same time, we increased the HEPA recirc air to maintain a total quantity of 20 CFM. But what we found out is as we dropped the outside airflow, humidity symptoms, irritation from humidity gets better, right? So the air gets more humid, but you start to get a buildup of gaseous contaminants to a degree. People are the primary source on airplanes. That's our highest density and strongest source of gaseous contaminants. We do off gas. What we found out is if we employ air purification, we're able to lower the gaseous contaminant level, but also maintain a higher humidity. And that actually gave us a preferred environment over just an aircraft that didn't have that type of technology. Next slide, please. So this is one of several slides. I only stuck just one of these in here, but there's, I think, over 6 pages worth of data. This is in-flight research done by EASA. EASA is the European regulator for aircraft, and they themselves did a big study. And the first two columns, the first column is just all the different volatile organic compounds, and they measured over 100 different types. Then the next two columns, I know that's small, so I'll just tell you what it is, and you can pull the study if you'd like. It's the mean and max value measured. And what they did is they took a bunch of measurements across Boeing fleet, across Airbus fleet, and then they went back and they particularly wanted to measure on the 787 aircraft, which is a more electric architecture. And if it's green, the final two columns are the 787, separated from the other data set. And if it's green, it means the 787 had lower volatile organic compounds. And what you see across the data set, the hundreds of some volatile organics, is the 787 was virtually lower on all the contaminants, from the mean to the max. Next slide, please. If you look across studies, so you go back a decade or so, so the Spangler, that's the big ash ray, 1262, we showed some data on that. Go on with some Chinese research, MHH, this is over in the Netherlands. Then the EASA, we just looked at some of that data. If you look at just a typical marker compound, toluene, 787 was lowest. But if you sum up the VOCs across decades of research, again, the 787 is lowest. And then you have to ask why. It's the only aircraft flying that has air purification basic on the aircraft. And that came out of the DT research. So I'm definitely would be an advocate to see the technology evolve onto other aircraft as well. I think everybody would benefit from that. APS was the prime factor improving air quality on that aircraft. Next slide, please. So if you look at the regulations today for air quality, the FAA, the Federal Aviation Administrator, the regulator here in the US for aircraft, specifies outside ventilation of 0.55 pounds per minute. Doesn't account for HEPA filters. It doesn't account for the air exchange rates or top to bottom airflow. It doesn't account for air purification. We can do better. I think the industry will move to performance-based regulations rather than just having a prescriptive one value. I think the future systems will be smart systems that'll have variable outside and purified airflow. And a really important part of these systems is going to be the filtration. It's going to be the particle filtration and the gaseous filtration as well. So you can optimize, you can have higher humidities, lower gaseous contaminants, you can improve the health symptoms, but you can also improve fuel economy and a greener airplane as well. And that is my last slide. So I appreciate your time.
Gentlemen, thank you. Some great stuff. We have some fantastic questions. David, we'll stay with you. A few people have asked what the preventive maintenance or filter change schedule is for aircraft. Is it set by magna helix and pressure drop, or is it set on a time-based schedule per hour?
So Boeing will give guidelines on that, but you can imagine if you're an East Coast shuttle flying 5 flights a day, you're going to have a different contaminant load than if you're an operator that's flying only, transatlantic type flights. Typically, the filters are changed out about every C-check, so about every 1,200 to 1,800 hours. So it's about once a year is typical. But some operators, lint is a big factor for life. So if you're doing multiple flights a day, you're going to be building up lint on those filters quicker. And so those airlines will change out their filters more frequent than those that fly transcontinental or Pacific flights. So that'll be, there's adjustments by the airlines, but typical 12 months, 18 months is a common for change outs.
Okay, we'll stay with you as well. Can you talk about when the airplane is not in motion and it's hooked up to the jetway? People are boarding, disembarking. What is the path while it's hooked up to the jetway for air filtration?
Yeah, so it depends on the airport, the airline. You can run the auxiliary power unit. It's a diesel unit at the back of the airplane that'll run the systems. But some airports have noise ordinances. Leonard Heathrow, you can't run the APUs at the airport. Some have ground carts that'll hook up into the belly of the airplane, into our mixed manifold for the outside air and the have a recirc air come together. You can provide air right at that location that then goes to the air distribution system. Or, as I think the question was asking, you can have conditioned carts on the jet bridge itself, and those will basically bring in the air at that vicinity, at the airport, and provide that air. I think that is an area that we can make improvements. I think that's an area that should be improved. I think sometimes the airflow is lower than what it should be. I think we need to maintain airflow on the ground as best we can. If you look at air quality studies, that is where the contaminants are highest, is during boarding and during deboarding. I think that's an area we need to focus on and bring. Some airports, some airlines do a really better job than others, and I think we need to bring everybody up to the same level.
I'm hoping they're concerned with not only particulate, but with gaseous contaminants.
Yes, yeah, because in and about airports, you're going to get, it's just like with buses and trains, you're going to get what's in that environment. And so there's going to be diesel exhaust, there's going to be engine exhaust as well.
Excellent. Dilution being not the solution, but on bus travel, what effect does opening windows have on the systems themselves, Richard?
And so it kind of plays into how clean is your outside air, and what are we trying to accomplish? Obviously, if someone sitting next to you on the bus sneezes and they have COVID or whatever, there's nothing your filtration system can do. But what the industry is really trying to do is convert those HVAC systems from a airborne pathogen spreader to an airborne pathogen removal type system. And so in combination with a mechanical air change, like opening doors, opening windows, ideally that would be good, is provided you have better quality air outside than inside. But on a lot of buses, you can't even open the windows. So
yeah, I've found that on metro buses, the windows don't open, and that on school buses, they do open. But then you've got the other issues related to, how much, what's the outdoor air like? But certainly if you can bring in outdoor air, and it's a good quality of outdoor air, it's always good to bring outdoor air in to dilute. It only helps, in addition to whatever you're doing from a filtration standpoint. The issue again is not only the quality of the air, but if we're bringing in large amounts of outside air and it's not to our design temperature conditions, then it puts an added load on the HVAC system that these buses are not designed to handle.
Super. Dan, United Kingdom recent study on trains evaluating the effectiveness of air filters on killing or eliminating airborne contaminants using chlorhexid. Has there been any studies like that in the US with additives?
I'm not aware of any. As I understand that, and correct me, but I understand that would be something that is penetrated into the filter fibers. So it would help kill something that is caught in the filter fibers, which is always good to do. You can either do that, or some systems actually shine UV lights on the filters as well to kill. But there's a lifetime that pathogens have when they're caught in filters, and that could be as many as sometimes as long as days. So it's good to do that. So I'm not aware of any studies.
Can you speak to the effectiveness of hydrogen peroxide plasma with improving indoor air quality?
I think the best way to look at that would be to follow what ASHRAE has given us on evaluating additive air cleaners, and follow either you could go to the Portland State University calculator online and use that, or you really need to, it's tough for people to break down that statement of, kills 99.9% in 30 minutes, and how do you do that? Well, you really have to know more about the lab test and know what size of container was that device connected to.
Another consideration with that is, where am I dispensing this, and is it a continuous thing? One I saw was, hey, we dispense it at the back of the bus. Well, if there's a threshold of how much I'm dispensing or whatever, if I need to get it to the front of the bus through diffusion, then I need to put out more in the back so that it gets to the front. Well, is it an appropriate level for the back of the bus, for the people in the back of the bus? And so those are just some of the questions. Now, others have ducted it through, and so then you get more diffusion, but just some things to consider.
Excellent. If we can ask all three of you, for planes, trains, and automobiles, what types of gas phase filtration are used in each segment of the business? Rich,
I can speak for the airlines or the aerospace. So we've actually tested. We went down to Lawrence Berkeley National Labs, and we did 7 years worth of testing of all types of active, passive, photocatalytic oxidation, catalytic, different types of passive technologies. And it's kind of like a HEPA filter, right? It's really hard to beat a HEPA filter if your system can take the pressure drop. It's hard to beat some of these new active carbon embedded woven mesh type filters from just effectiveness and simplicity of plug and play. You can put it in, it works for a period of time. You pull it out, and you put another one in. And that's what we're doing right now.
I think on passenger rail cars, I've seen probably pre-COVID, MERV 7 or MERV 8 filters were used. And again, they have outside air that's brought in, similar to commercial buildings. I've seen MERV 13 being used. And I think Rich mentioned, we both were made aware of a very large rail provider that was actually, as they moved to MERV 13, because of the pressure drop, like David mentioned, that they were actually changing their filters out on a weekly basis in order to not impact the HVAC system performance. On buses, Rich showed us a slide earlier of the filters that are typically in metro and school buses, and those are either usually MERV up to maybe MERV 4, which, the filters predominantly have been there just to try to keep the HVAC systems clean as much as they can. They haven't been used, pre-COVID anyway, thought of as how can we improve the air quality in these spaces, especially in buses.
Excellent. Difficult question. Is there legislation federally or locally that mandates any type of filter requirements for any of these systems?
I've yet to see that, and I hope that's part of what this presentation does with the National Air Filter Association is that we have an impact on our public health officials, and we get that word out. With so many people using public transportation, it's good to see that in airplanes that the job's done so well. But there's a continued reliance on other ways of mitigating disease transmission, like vaccines and so on. The nice thing about a filter is that, and by the way, it's been very successful. A filter doesn't care what the spike protein looks like. It doesn't care whether it's a previous version of MERS, SARS-CoV-1, H1N1 flu, or God forbid, whatever happens next to us. It's just going to take it out of the air. So that's the nice thing about filtration, and it can be put in there. And you know, I think hopefully we can advance our world to where we're all able to breathe clean air, just like we make the assumption, at least in the United States, that we're going to drink water in a public space. We're drinking clean water.
Perfect. I think that sums it up for everybody. Antimicrobial filters. Do you see the need for these in any of these three applications?
We've looked at them on aircraft, you know, so basically kind of a coating you put on the filter. It seems one challenge is once you start to build up a dust cake on that filter, which you do just after, you know, a few hundred hours, you're now separating anything that's coming in contact with that filter from that coating. And so we haven't been, we don't have that on the aircraft filter. I think it can be purchased as an option, but that's not something we see as a real benefit, simply because as you start to build up the dust cake, any particles that are coming on get removed by other particles that are on those filters. And the new particles coming in don't come in contact with the treated fibers themselves.
It's pretty much the same on bus and train. And again, you're dealing with a mindset that used to be, as Dan said, we're looking for that cheapest option to keep the equipment clean. So it's not much for effectiveness, and I really haven't seen it.
Okay. Any real-time particle monitoring going on with concentrations of particulate or gaseous substances?
I know there's studies going on, funded publicly by different universities. There have been a few. There's one in Colorado that looked at filtration on school buses. There is some information out there, and I think as many people that use public transportation, it should get even more funding and more analysis.
I would agree with Dan on the aerospace as well. There is research going forward, sponsored by the FAA. EASA from Europe has also sponsored some research looking at different types of sensor technologies.
Any recommendations on disposal of filters from any of these, or any actual knowledge on how they're handled during the preventive maintenance schedules?
So for aircraft, there is guidelines on treating the filters as hazardous material. So you have to wear gloves, you have to wear, the proper breathing filters. Just because after 12 months, that's a lot of biological material, and so it's there is guidelines for that to change out those filters.
I think on the rail and the bus side of it, it's more of not a national, or even, I haven't seen any state regulations either. It's more of a individual policy based on the organization.
Okay. Quick question for Dave. Someone asked how the air is sourced, how outside air gets into the airplane. You could describe that path.
So for most aircraft, 787 is an exception. It comes in through the engine compressors. So upstream of the combustion chamber where fuel is added. So the air comes in, it goes through a compressor. It's compressed to very high temperature, 450 degrees Fahrenheit, 45 PSI. It's pretty typical. It then flows down ducting to the what we call air conditioning packs, and it's basically a package of compressors and turbines and valves and such that cool that air down to the required temperature to then be provided into the cabin. So typically, believe it or not, airplanes are quite often in a cooling mode because of the high density of people and the in-flight entertainment. So the air is cooled down to 60 degrees is not uncommon, and then that's what's then mixed with the HEPA filtered recirc air up to the overhead air distribution system, and then distributed into the airplane cabin.
Excellent. Gentlemen, we're at our time. We've answered a ton of questions. I'm sure there may be more. Tony, if you want to take over from here and describe the path of how we could get some more questions answered, I'm sure the panelists would be able to help with that. And gentlemen, thank you very, very much on behalf of NAFA.
Fantastic job. Thank you
Thank you.
so much, guys. Absolutely. David, Richard, Dan, and Jeff, thanks so much for an awesome information. If you'd like, you guys can let me know later, but if you guys want to answer any follow-up questions, we can make sure we collect your contact info and put people in touch with you either via social media or email, and I can make that available. So just let me know either now or later. And then just let people know we will we have recorded this. We'll put this up on our YouTube channel. We'll put this up on our webpage. Please like and share it with anybody you think should see this. If you missed this, we emailed you, and you'll get a link to this. If you want to watch this again and you were here with us, we'll email you also as well a link to the recording. The slides will be available as well. And if there's any other questions, you go ahead and shoot them over to us here, and we'll make sure that the panelists see them. Or again, we'll make sure that the panelists are available as well through that webpage to connect there. Thanks so much. Any other final thoughts or questions, guys, or comments, I should say?
I learned so much over the last 10 days talking with you guys, so greatly appreciate it. Some great points, and each transportation vessel is treated independently because of outdoor conditions and space requirements for equipment and filtration, and just some awesome information. So thank you guys for sharing.
Thank you.
Thank you.
Fantastic. Well, again, follow, like us. You can go to our website, join our page, or join our mailing list, I should say. In July, the Education and Training Committee is planning on conducting another webinar on the new requirements in K through 12 school facilities, which should be an excellent webinar as well. So we will collect a few folks that know about those sorts of things. And so if you are interested, if you have a expertise in that, please contact us, reach out to us through any of these channels, and we'll be happy to possibly put you on our docket for that. We do all kinds of education in all these kind of spaces, in travel, in public spaces, and other applications. So check out our website, check out our education, and please engage with us. With that, we've been talking air filtration with David Space, Richard Gillick, Dan Fillenworth, and Jeff Thibodeau. Thanks so much. I'm Tony Verhoeven.